I'm excited today to get into our mechanics lab. Finally, you're going to get to break something and do some kind of really fun things in the lab. Unfortunately, we can't do that because we're not in person, but you'll get to kind of see me and then hopefully live vicariously through me. So we are going to be looking at several materials: aluminum, copper, high-density polyethylene, and polystyrene. High-density polyethylene is a semi-crystalline material, semi-crystalline polymer. So as you might expect in your XRD plot, you'll see multiple peaks, not as sharp as these metals. XRD is a function of theta. You just have these delta functions. But polystyrene is amorphous. It's like a spaghetti structure. And that is going to look quite different. So it's going to have a broader perspective. Now, due to these differences in structure, you're going to see some vastly different properties. And the same thing for aluminum and copper as well. So we are going to be measuring these in a uniaxial tensile test. So we're going to have these basically these grips and these claws. So I'm going to actually draw a little bit nicer. So we have these grips, and so there's going to be kind of a little space here. And then we're going to put our sample in between these grips. So we're going to put our sample, our dog bone sample, so it's going to have some geometry like this and thin. You're going to see it in just a second, but you'll see it in the video as well. We're going to put a sample like this, and we have our units, or our kind of coordinate system, so 1 and 2. So we're going to pull up in tension. So we're going to have in our stress tensor, it is the simplest case, the only time when you could really use our kind of Young's modulus instead of my other most favorite, our the equation that we all know and love so much. Our epsilon ij is equal to 1 over E times I'm gonna where I'm going now. Ij what's new here minus nu sigma kk of delta. But anyways. So we won't be using this one, unfortunately, for this experiment, because in our stress tensor, looking at this coordinate system, we're going to have 0, 0, 0, 0, stress in the 2, 2, 0, 0, 0, 0. So that's kind of the stress tensor that we're working with. So we're going to pull out that sample. We're going to look at and measure these different properties: the modulus, tensile strength, yield strength, elongation of failure, elastic strain energy, toughness, and we're going to basically generate these stress strain curves and calculate these values. So we're going to have a load cell. So a load cell is essentially, in our experiment, we're going to see on it's going to kind of generate that force. We're going to pull it at a specific strain rate, 15 millimeters per minute. So that's going to be our strain rate. We're going to measure the stress, strain. Again, hopefully this all looks very similar from our lecture notes. We're going to see the elastic regime, plastic regime. We're going to kind of calculate all of these values of sigma y, this, strain at failure, what's my UTS, what's my yield strain, what's my Young's modulus, what's my toughness, my energy here. So these are all the things. When does, we see again right here, that's where our necking occurs, and you're going to see kind of the necking and the thinning basically occur in this experiment. And then eventually the kind of most exciting part, not corrosion, but instead fracture. So again, we're going to measure all these different properties, but it's like a very, very, very fun experiment, very, very simple experiment. We're going to have an instron, calipers, extensometer. So this is essentially what I was talking about previously. So this is our load cell. So we have a 50 kilonewton load cell. So we can only generate forces as large as 50 kilonewtons. Luckily, that's enough to kind of break our samples. So these are the grips that I was talking about. And then again, with our kind of apparatus here, we can go ahead and pull at different strain rates. So we're going to pull at 15 millimeters per minute. We have these cylindrical versus rectangular draws. So ours are flat samples. So you're going to kind of measure, and you'll see the kind of dimensions in our PowerPoint slides as well. The dimensions of our sample, and then we're going to go ahead and then calculate the strain from that. So again, we're pulling at 15 millimeters per minute. Well, the test will stop, excuse me, once the force drops by 40%. So when the material fractures, essentially. And we'll also clip on, excuse me, an extensometer. So on your material, you can clip on an extensometer, which is going to basically measure the strain in that material directly. So you'll get the data that's on that, and you can kind of see as I do that in the experiment in the next video coming up. So we're going to do that. We're going to export the data, and then we'll analyze that in another video. So just to give you kind of an idea a little bit more. So we know the stress strain curve. We've talked about it, quite a bit in class. We see kind of where that necking is going to occur, which is going to be right around there. So it thins, and then eventually fracture is coming. So we know that ceramics are brittle, and basically elastically fracture. There's no ductility. Metals, polymers are much more ductile. We could see kind of these different mechanisms of yielding, shear banding, and crazing in polymers. It's kind of hard to see it in our particular polymers, but you can see it a little bit. And then again, our really, really nice apparatus. So these are the dimensions of our sample. So you could calculate the volume from this. You could kind of just assume it's completely. You could make an overestimate, or you could do if you want to do the geometry, but we could just assume it's a 6-inch by 1/8 inch, and then it's 1 inch here. So we can calculate the volume. Why do we need the volume? Because we need to eventually calculate the toughness. And again, we kind of measure essentially this different gauge length here. So we have a gauge length. This is our gauge length. It's 4 inches. So we in this lab, we are going to calculate, and we're basically going to create stress strain curves. We're going to measure all of these different properties here, and then discuss kind of some of the differences and see kind of some of the really, really cool different behaviors that you see based on the different properties. Excited. I wish we could be there in person. This is why you become a material scientist. But anyways, I'll see you all in the next video. Thanks. Bye.